Hey, do you know what a signal is? A signal is essentially a way to represent information about changes or variations over time, whether it's sound, light, or other types of data. Signals can come in different forms such as electromagnetic, optical, or acoustic. In audio signal processing, we start with acoustic signals, sound waves captured from the environment. These sound waves are converted into continuous analog electrical signals and subsequently into discrete digital signals for analysis and manipulation. Digital signals are preferred because they are easier to store, process, analyze, and extract features, making them ideal for tasks like speech recognition. All right, let's see how that transformation happens. The process of converting analog to digital signals consists of two main steps: sampling and quantization. We'll uncover these terms specifically in the context of audio signals. Sampling captures multiple snapshots of an analog signal's amplitude several times per second. In fact, not just several, but thousands of times. You may know that standard CD quality audio is sampled at 44.1 kHz, capturing the signal's amplitude over 44,000 times per second. This measurement frequency is known as sample rate. Each snapshot measures amplitude at that instant, though the data remains analog. To digitize it, we apply quantization, which rounds each sampled amplitude to the nearest value within a predefined set of discrete levels. Suppose you have a ruler marked with only whole numbers and must measure something that falls between two marks. You would round your measurements to the nearest whole number, right? Similarly, in quantization, each amplitude value is rounded to the nearest level that can be represented digitally. For example, an 8-bit system allows for 256 possible levels, 2 to the power of 8, to round amplitudes. This concept, called bit depth, refers to the number of bits representing each audio sample. The higher the bit depth, the more levels are available, allowing for a more detailed representation of the original analog signal. Following this, bit rate, which measures data processed per second and combines bit depth and sample rate, determines the audio file's overall quality and size. The file's bit rate is calculated by multiplying the bit depth by the sample rate by the number of channels in the audio file. A channel is simply an individual audio track within the file, such as the left and right tracks in a stereo recording or a single track in a mono recording. For example, if you have a stereo audio file with 2 channels, a sample rate of 44.1 kHz, and a bit depth of 16 bits, the rate would be 44.1 times 1000 times 16 times 2, resulting in approximately 1,400,000 bits per second. In other words, the audio file processes roughly 1,400 kilobits of data per second, influencing the sound quality and the file size. Okay, let's summarize what we've learned. The sample rate determines how frequently the audio signal is sampled per second. Increasing the sample rate enhances audio clarity and accuracy, helping the speech recognition model distinguish delicate speech-sound differences. Bit depth affects the precision of each audio sample. A higher bit depth captures audio amplitude more accurately, enhancing clarity in softer and louder speech elements. This precision is crucial for discerning speech nuances like tone and accent variations. Bit rate combines sample rate and bit depth to indicate the overall audio data processed per second. It affects both the quality and the file size of the audio data. Understanding bit rate helps balance audio quality and computational efficiency, which is vital in real-time speech recognition applications, where both high accuracy and low latency are desired. Good. So, thanks to sampling and quantization, continuous amplitude values are transformed into a finite set of digital numbers that digital devices can process and store. This allows various mathematical manipulations of the digital signals, or in other words, digital signal processing. We'll talk about digital signal processing in terms of audio in the next lesson. See you there. Hi again. Let's use our knowledge about digital signals to explore how they can be manipulated and used for different purposes. Digital audio signal processing can involve various operations depending on your goals. As a music producer, you'll want to manipulate signals to enhance tracks with cool effects and improve the final mix. If you're an audio engineer, you might focus on removing noise, improving equalization, filtering, and applying correct compression to prepare the sound for an audience. These manipulations are types of processing. Now, shifting fields, if you're a data analyst, scientist, or machine learning engineer, your main goal would probably be to transform raw audio data into a format that machine learning models can efficiently process and learn from. Speech recognition models are built by training on vast amounts of processed and well-prepared audio data, which helps the model learn to effectively identify patterns and features in speech. So let's look at the steps a data scientist or an ML engineer might take when processing a digital signal. Pre-processing. The initial stage in preparing audio data for ML model training or transcription primarily focuses on eliminating background noise to improve signal clarity and quality. This enables models to recognize words and patterns with better accuracy. While cleaning noise is essential for improving audio clarity, it's also crucial for models to learn from noisy data. Training on such files helps models become more robust and better at recognizing speech in real-world conditions. The key is balance. Pre-process audio to eliminate distracting noise while preserving natural sounds in the training data. This way, the model learns to effectively handle clean and noisy audio, improving its performance across different environments. Normalization is another pre-processing step that involves adjusting the signal level to maintain consistency across different audio samples. It minimizes variations in volume, allowing the model to compare audio samples more accurately. In other words, normalization ensures that the volume of audio files is similar across different files, helping the model learn more effectively. Resampling means changing the sample rate of an audio signal to match the requirements of a machine learning model or a specific application. Different models and tasks may require different sample rates, and resampling ensures compatibility and consistency. This step is crucial when combining datasets from multiple sources with varying sample rates, or when the model is optimized for a specific sample rate. Data augmentation is used to increase a dataset's diversity without collecting new data. Data augmentation in digital audio processing involves creating new audio samples from existing ones by applying different transformations. This can include adding background noise, shifting pitch, altering speed, or applying effects like reverberation or echo. These transformations help create new audio samples from existing ones, improving model robustness and performance, especially when training data is limited. Segmentation is the process of identifying and isolating sections of audio where speech is present. This step is vital for tasks like speech recognition, where only the spoken parts of an audio file are relevant. Segmentation can also break down longer audio files into smaller, more manageable segments for easier analysis and processing. Compression involves reducing the audio data size while preserving as much of the original quality as possible. Compression can be lossless or lossy, depending on the application's requirements. In machine learning, efficient data storage and transmission are essential, and understanding how to compress audio data effectively can play a significant role. Feature extraction is extracting relevant audio features for machine learning models. Spectrograms are a popular visualization tool for this purpose, showing the frequency content of an audio signal over time. Understanding the frequency distribution helps in speech recognition by highlighting the key characteristics of speech sounds. Spoiler alert, we'll talk about this in more detail later in the course. Let's take a break for now. See you later. Welcome to this section on audio features. So, what exactly are these? Audio features are distinct properties of sound that help us analyze and interpret audio signals. These features represent qualities like pitch, the highness or lowness of a tone, loudness, sound volume, rhythm, temporal sound patterns, and timbre, distinctive tone or color. By extracting these features, we can teach machine learning systems to recognize speech and other patterns within the audio, making it possible to identify words, sounds, or even emotions in speech. Great! In this course, we'll use pre-trained models to convert speech into text. To truly harness the power of these models, it's essential to understand the underlying processes. Knowing how the algorithms operate will give you a stronger foundation to use them effectively in real-world applications. This is why we'll examine the various audio features that play a key role in processing and recognizing speech. Later in the course, we'll explore specific parameters related to these features, giving you hands-on experience in fine-tuning the models for even greater accuracy. You'll gain technical insight and develop a deeper appreciation for the richness of sound and the fascinating journey behind the discovery of speech recognition algorithms. So let's get started and learn what audio features can be and how they play a crucial role in enhancing the performance of speech-to-text applications. Okay, audio features can be split into the following categories: time domain, frequency domain, and time-frequency domain. Each category provides insights and specific purposes in audio signal processing and machine learning tasks. We'll dedicate this lesson to the first category, time domain audio features. Time domain features are extracted directly from the raw audio waveform, examining volume fluctuations over time to discern patterns and changes. This approach reveals crucial information about the sound's behavior, such as its start, stop, and variations in loudness. Let's look at some of the most famous time domain audio features, starting with zero crossing rate, or ZCR. Sounds fancy, right? But this feature simply counts the number of times an audio signal switches from positive to negative. Imagine a sound wave moving up and down. Each time it crosses the middle or zero line, it changes from positive to negative or vice versa. The zero crossing rate calculates how frequently this occurs for the entire audio or specific segments. The term rate denotes the frequency of zero crossings within a specified time, measuring how often the signal changes direction. ZCR is directly related to the frequency of a sound. A high ZCR means the sound crosses the zero line frequently, indicating high frequency, while a low ZCR shows fewer crossings, which is typical for lower frequency sounds. In speech recognition, ZCR distinguishes between voiced sounds like vowels with low ZCR and unvoiced sounds such as consonants or background noise with high ZCR. Since noise often has a high zero crossing rate, it can be identified and filtered out, helping the system focus on actual speech. By recognizing where speech occurs and breaking it down into smaller units like phonemes or words, ZCR improves the accuracy of speech-to-text conversions. Alright, next comes the root mean square, or RMS energy. This metric helps estimate the average signal amplitude value, representing how loud or energetic the sound is over time. Amplitude, however, can be either positive or negative. So, how do we calculate its average if it's constantly changing? The solution is simple. Square each value to ensure positivity, average these squares, and then take the square root of the result. This gives us the RMS energy, crucial for identifying and differentiating speech from silence. Cool, eh? The next feature we'll discuss is the temporal centroid, which indicates the middle point of a sound's energy in a recording. Consider a song that begins gently, builds to a robust chorus, and then softens. The temporal centroid would lie near the chorus, where the sound's energy peaks, harmonizing the quieter sections at both ends. It's like balancing a seesaw with equal weight on both sides. If the song isn't symmetric, meaning it doesn't have evenly distributed quiet and loud parts, the temporal centroid will shift accordingly. It may not be in the middle of the clip, but closer to where the song is louder for longer. For instance, if a song begins softly but predominantly remains loud before quickly fading, The temporal centroid will gravitate towards the louder section, its center of loudness, like a seesaw tips towards its heavier side. This flexibility helps identify the most prominent sections of any sound, even when the loudness is unevenly distributed, making it helpful in recognizing key speech parts in less structured audio. Excellent. The last time domain feature we'll discuss is the amplitude envelope, which shows how a sound's loudness changes over time. In simpler terms, amplitude envelope tracks how the volume goes up and down as the sound plays. In speech recognition, this helps identify different parts of a word or sentence, such as when a word begins, gets louder, and fades away. Imagine pressing a piano key. The sound begins, remains loud briefly, and then gradually diminishes. These phases, attack, sustain, and release, form the amplitude envelope, illustrating the sound's loudness. Great! We've covered some of the most fundamental time domain features for speech recognition. We've talked about the zero crossing rate to distinguish noise from speech, RMS energy to measure the average loudness, temporal centroid to find the energy's balance point, and amplitude envelope to track changes in loudness. These essential features lay the groundwork for understanding audio. The next lesson will explore frequency domain features. See you then. Hello. Last time, we discussed time domain features which focused on how the loudness and energy of a sound change over time. Now, let's move on to frequency domain features, which help us understand the different tones and frequencies present in the audio. Frequency domain features are created by converting the audio signal's changes over time to how it spreads across different frequencies. In other words, instead of looking at the signal over time, we look at the different tones that make up the sound. Let's explore some of the main frequency domain features. The spectral centroid tells us where the center of mass is in a sound's frequency range. In simpler terms, it helps pinpoint the middle of the sound's energy in terms of its tones or frequencies. You can think of it like the temporal centroid, but instead of finding the balance point based on loudness over time, the spectral centroid finds the balance point based on different frequencies, which is why it's typically measured in hertz. If a sound has more high-pitched tones, the spectral centroid will be closer to the higher frequencies. And if it's deeper, it will shift toward the lower frequencies. Imagine you have a sound that includes low and high notes, like a mix of bass and treble. The spectral centroid helps us determine the average pitch where most of the energy is concentrated. If the sound has more high-pitched notes, the spectral centroid will be higher, making the sound seem brighter. With more low-pitched notes, the spectral centroid will be lower. For example, in a rap song, the bass and kick drum beat typically has lower frequencies, so the spectral centroid would be lower during those parts, giving the song a darker or deeper feel. Alternatively, if higher-pitched sounds such as hi-hats or certain synths are present, the spectral centroid would be higher, creating a brighter sound perception. In the word boom, the deep-voiced b and m sounds result in lower spectral centroid. In contrast, in the word hiss, the unvoiced h and s sounds are higher pitched, resulting in a higher spectral centroid. These clear distinctions help the speech recognition system better identify and categorize the different sounds in each word. Interesting. Next up is the spectral bandwidth, which measures how wide the range of frequencies is in a sound. In simple terms, it tells us how spread out the frequencies are. A narrow spectral bandwidth indicates concentrated energy at few frequencies, which is typical of simpler, smoother sounds like pure tones or steady vowel sounds. A wide spectral bandwidth indicates a broader range of frequencies in noisy or complex sounds. Spectral contrast measures the difference between a sound's loud and quiet parts based on its different frequencies. This means it examines the energy present at various pitches, low to high, and compares the loudest and quietest parts within those frequency ranges. Think of it like a mountain range. The peaks are the loud, high-energy parts, and the valleys are the quieter, low-energy elements. Spectral contrast tells us how big the difference is between those peaks and valleys. If the peaks are high and the valleys are shallow, the contrast is high, meaning the sound is more complex and rich. This feature is helpful because higher spectral contrast can indicate more detailed and varied sounds, like speech with many different tones, while lower contrast can suggest simpler, smoother sounds. All right, time and frequency domain features exist, yet there are also time-frequency domain features. Unsurprisingly, time-frequency domain features represent the signal in both time and frequency domains, capturing how the signal's spectral content changes over time. Mel-frequency cepstral coefficients, or MFCCs, a type of audio feature, are notably intriguing. They depict how sound energy spreads across frequencies, tailored to our ear's sensitivity rather than treating all frequencies equally. Here's how it relates to human hearing. Our ears are more sensitive to specific frequencies. For example, we hear middle frequencies where most speech happens much better than high or low frequencies. MFCCs utilize the Mel scale to space frequencies in a way that aligns with our natural hearing. This approach makes them particularly effective for speech recognition because it enables the system to process sounds like human hearing. Imagine listening to someone speak. Your ears naturally focus on the middle frequencies where speech is clearest, while higher-pitched sounds like a whistle or very low-pitched sounds like a distant rumble are less audible. MFCCs help a computer do the same thing. The Mel scale allows the system to focus more on the critical frequencies for speech, just like your ears do when listening to someone talk. This helps the computer recognize and understand speech more effectively. Okay. To wrap up, we've explored key frequency domain features like the spectral centroid, spectral bandwidth, and spectral contrast, each of which helps us understand sound's different tones and complexity. We also introduced time-frequency domain features such as MFCCs, which mimic how human hearing focuses on essential frequencies. These features are crucial for speech recognition because they enable systems to process sound more effectively, just as our ears naturally do. Understanding these concepts sets the stage for improved audio management across applications, particularly speech-to-text technologies. In the next lesson, we'll explore the theoretical concepts of audio feature extraction. See you there. Hi, and welcome to this exciting lesson on feature extraction for speech recognition models. Feature extraction is one of the most fascinating processes in speech recognition because it involves taking raw audio and breaking it down into meaningful data that machines can understand. This process is not just technical, it's where the magic happens, transforming sound waves into patterns that enable machines to recognize speech, interpret commands, and even interact with us naturally. Learning feature extraction will provide valuable insights for making better decisions when choosing or customizing speech recognition tools. You can ensure these tools meet your needs for accuracy and reliability. And finally, you'll be one step ahead of others in understanding how these systems truly work, giving you an edge in fine-tuning and optimizing their performance. You'll grasp how existing models work and gain inspiration to explore building your own machine learning models for speech recognition. It's a crucial step in harnessing the full potential of these technologies and shaping the future of human-machine interaction. Okay, let's start our journey considering how time-domain audio features are extracted. Feature extraction begins after the signal is converted from analog to digital, a process we explored earlier in the course. To convert an analog sound to digital, we measure the sound wave at frequent intervals. Each measurement is called a sample and captures the loudness or amplitude of the sound at that specific moment. Okay? Understood, right? Once we have digitized the sound, we need to organize the samples by framing, which involves grouping samples into small chunks for more straightforward analysis. For example, frame 1 can include samples 1 to 128. Frame 2, 64 to 192. Frame 3, 128 to 256, and so on. This overlap helps ensure that no crucial details are lost between frames. But why do we need framing? Let's consider our first chunk, which contains samples 1 to 128. Each of these samples represents a tiny snapshot of the sound, but on their own, they're too short to be meaningful for analysis. This is where framing comes into play. By grouping these small samples into frames, we create chunks of sound long enough to capture essential patterns and features. Think of it like reading a book. A single letter or word doesn't give you much information, but the meaning becomes apparent when you group enough words into a sentence. Similarly, framing in audio helps us gather enough data to identify critical patterns like pitch, rhythm, and tone, making it easier for speech recognition models to understand the sound. So, what's next? After framing, the next step in feature extraction is called feature computation. This involves calculating each frame's time domain features by analyzing its specific characteristics. Recall that time domain features describe how the signal behaves over time and how sound changes from moment to moment. Next, the features from each frame are combined to represent the entire sound we're analyzing. This is done using simple calculations like finding the mean or median of all the frames or more advanced methods. The process gives us a final set of values that act like a summary or snapshot of the entire audio signal, capturing its key characteristics over time. Okay, great. So we convert the original analog signal into digital format. Divide the digital audio into frames with samples. Extract the time domain features for each frame. And finally, use statistical tools to aggregate these features and obtain a snapshot of the entire audio. This is how we extract time domain audio features. It might sound complicated at first, but don't worry, there are many Python libraries and tools that can do these procedures for us. Additionally, most recent models can automatically extract the required features on their own. And thanks to this theoretical knowledge, you'll be well aware of what happens behind the scenes. Cool. In the next lesson, we'll see how the process works with frequency domain features. See you then. The process of extracting frequency domain audio features is similar to what we do with time domain extraction. The first two steps are identical. We begin with the analog to digital conversion to obtain a digitalized version of the audio signal, and then frame the signal into groups with samples. Next, we convert our sound from the time domain to the frequency domain. This entails transforming the signal's initial time amplitude representation into a frequency magnitude format, revealing the contribution of each frequency to the overall sound. We typically use the famous Fourier Transform, named after the influential French mathematician and physicist Jean-Baptiste Fourier. But why isn't the time domain representation sufficient? The time domain representation of audio only shows how the sound's loudness changes over time. It doesn't give any information about the frequencies present in the sound, which are critical for recognizing speech patterns like vowels, consonants, and pitch. Without converting the sound into the frequency domain, we miss the essential information. So let's briefly explore the Fourier transform with an example. Consider a complex sound such as a guitar chord. We call it complex because it blends multiple frequencies, not just one. A chord includes several different notes played simultaneously, each with its own frequency. Through a series of mathematical operations, the Fourier transform can almost magically break this signal down into its notes, showing the different frequencies and their magnitudes. It achieves this by analyzing the contribution of each frequency or note to the overall sound. So, the Fourier transform breaks down a chord to show each note and its intensity or volume. It's like turning a jumbled sound into a clear picture of all the frequencies, allowing one to understand the different components of the sound. This process is known as discrete Fourier transform, or DFT. It's beneficial because it helps us understand the different components of a sound, making it easier to analyze and manage audio for tasks like speech recognition. DFT breaks down digital signals into their component frequencies, but does not reveal how these frequencies vary over time. For this purpose, we use the so-called short-time Fourier Transform, or STFT. Unlike the DFT, which provides a single frequency spectrum for the entire signal, the STFT gives a time-frequency representation, showing how the frequencies vary at different points in time. It's crucial to determine which frequencies are present and when they appear in the signal. In speech recognition, the STFT identifies phonemes and tracks changing speech features over time, pinpointing and filtering noise at specific times and frequencies. Consider a song recording where both the vocals and instruments evolve throughout. The DFT provides a general overview of the song's prevalent frequencies. The STFT lets you track frequency content changes over time, revealing which notes are played, how the singer's voice shifts, and when instruments enter or exit. STFT is essential for analyzing signals and understanding the dynamic nature of their frequency content over time. It provides a more comprehensive view than the DFT. Nevertheless, as you'll see in the practical part of this course, both Fourier transformations are essential for audio processing, feature extraction, and speech recognition. Okay. We now understand how audio feature extraction works, what it requires, and why it's necessary. We've also explored the basics of the famous Fourier Transform, a crucial step in audio and signal processing. This vital foundation is vital for understanding speech recognition technology. In our next lesson, we'll use this newly acquired knowledge to explore the basic mechanics of acoustic and language modeling, the hidden procedures behind speech recognition. See you there.